now be present the beta paper, which introduces a binary transformer accelerator for edge devices, aiming to reduce energy consumption and increase speed without sacrificing accuracy. So let's start from background. Transformers are widely used but heavy, making them hard to deploy on edge devices. Binary transformer reduce computation, but most existing hardware is optimized for full precision. Or modern quantization, which wastes resources when running binary models. The binary transformer used 1 bit wait and low bit activation. This reduces memory and speeds up the operations via bitwise multiplication. The challenge is supporting mixed precision operation efficiently, especially quantized matrix multiplication, or QMM. So let's look at the graph. This is a vanilla block and this one is a binary block. In the vanilla block, both MHA, which stands for multi-head attention, and FFN, which stands for feed-forward network, they use the full precision wait and activation. This allows high accuracy but consumes a lot of memory and computational power. On the other hand, the binarized block, the wait and the activation is just 1 bit. Oh no, the wait is 1 bit, and for the activation it's typically 2 to 8 bit. Both the MHA and FFN computation now leverage the integer or bitwise operation, drastically reducing storage and computation. The key difference is that binary blocks are hardware friendly, enabling fast and energy efficient inference on edge device, while vanilla block relies on heavy floating point operation. Beta use a key technique called computational flow abstraction to save energy. In binary transformers, each activation or wait is stored as a small integer with scaling factor and offset, which is representing like this. If we naively multiply 2 matrices, required full precision multiplication for every element, which is expensive. Beta expanded and reorders, so now we can see the A multiplied by W. This one is a integer multiplication instead of like a full precision multiplication. Only a few small precision multiplies in the remain. This reduces energy by tens or hundreds of times while keeping accuracy high, making beta efficient for edge devices. If we look at the complexity, this reduced from n cubed to n squared. So the QMM engine handles most computation. We will talk about it in the next graph. While the VPU applies full precision coefficient and offsets. Nonlinear functions like softmax and GELU are processed in full precision as they are less computationally intensive. On-chip buffers and an MCU handle input storage and control signals, ensuring smooth data flow and high efficiency. The QMM shown in this figure consists of multiple dot product or DPUs, which is like here, dot product unit. Each DPU has a PE sequence, which is here, that performs parallel multiplication and a compressor tree loop, which is here, the compressed tree loop, that efficiently sums partial results. To increase the parallelism with a vector, beta uses unfolding, so each DPU can handle multiple elements simultaneously. Finally, a carry select adder combines the partial sum into the final result. By tuning the number of DPUs and the unfolding factor, beta can flexibly balance throughput and resource usage. So this figure illustrates the operation modes of beta's configurable PE sequence. The PE sequence can adapt to different combination of weights and activation precision. It uses two key techniques: data packing, which allows multiple multiplication to be combined into one PE output. And a bit serial traversal, which processes multi-bit activation sequentially when necessary. For example, in W1A4 mode, 1-bit wait and 4-bit activations. Two multiplication are executed simultaneously and packed into an 8-bit output in a single cycle. In a 4-bit activation and a 4-bit activation mode, like 4x4, the PE processes one operand bit by bit across 4 cycles to generate a final result. The flexible PE design enables beta to efficiently handle different QMM types and activation precisions while maintaining high throughput. This is the experiment result. Beta was implemented on an FPGA and tested on state-of-the-art binary transformers. Latency and power were measured using simulation and power tools with CPU and GPU result for comparison, using a single sample per batch to mimic edge condition. Results show that the lower activation precision increased throughput and energy efficiency with minor accuracy loss. Beta outperforms previous FPGA designs by 22 times and achieves hundreds of times better energy efficiency than CPUs and GPUs. Beta's main contribution are the computation flow abstract we just mentioned before, a configurable QMM engine, high parallelism, and the ability to dynamically adjust activation precision to balance efficiency and accuracy. In conclusion, Beta demonstrates how binary transformers can be deployed efficiently on edge devices, supporting multi-precision operation with high parallelism, achieving impressive energy efficiency and throughput compared to prior FPGA, CPU, and GPU solutions. That's all for this week. Thank you.